People keep streaming in for another minute or so. We'll get moving. Okay. Okay, I will get moving. Yeah, like class today, I'm not too surprised. It's the end of the term. Hello, friends. Thank you for coming to the last lecture of the term. It's very sad. I'm going to miss everyone, even if it's still weird that I communicate with people only over a video chat with most people's screens turned off. Anyway, yeah, so today is kind of a mixed lecture. Yeah, this isn't my last lecture. I'm actually teaching in the spring still. So I technically have one more term. Well, I'm actually teaching next term and I'm teaching in the spring. So spring will be my last time I ever teach this class. So that will be the 9th or 10th term I've taught this class in the spring. So, been doing it a while. But yeah, anyway, today is a mixed lecture. This used to be 2 separate lectures and I kind of chopped it down a little bit. So it's kind of split in the middle. The first half is going to be model results. Model results is basically how do we take all this output you're going to produce in every other stats class you do here at UW and turn it into something pretty usable or interpretable in a way that's not as hard as what they probably teach you in those classes. Okay, turns out it's pretty easy to do a lot of that stuff. And then I'm going to ramble about reproducible research and good practices for like 30 minutes after that. And there won't be a lot of code. There'll just be a lot of me screaming about what people should do to make science better. Okay, so that's what we got. So this is what it looks like today. We're going to be working with model results. I'm going to talk about tidying up models with Broom. That is making model results turn from lists into nice data frames, how to visualize model results with ggeffects, and how to make tables with a variety of different packages. Talk about reproducible research, talk about best practices on organization, portability, and version control of your projects. And then we'll just kind of wrap up a little bit, sort of reiterate what we covered in the class and suggest next steps for people at different sort of stages of their career. Okay. So first thing is working with model results. So Broom is a handy little package that I think gets installed by default when you install the tidyverse. Broom is a package that tidies up output from models you run. And it tidies up the output from almost every imaginable package. All the common packages and even fairly niche packages can be tidied up using Broom. So Broom has 3 main functions in it I'm going to talk about. The first one, tidy, is the main one. What tidy does is you give the output from a model, like an LM model or a GLM model or something like that, you give it to tidy and it digests that ugly list output that we all hate dealing with and turns it into a nice data frame. Okay. Then the functions, which I use a lot less, augment and glance. Augment, you will run a model and then augment your original data. And this will add things like fitted values to your original data, but also leverage statistics and stuff like that. This is really nice because it's a lot easier than going and like manually calculating leverage statistics or something to add them onto a data frame when you can just pull the trigger, press one function, and it spits everything you want out. Next is glance. Glance is sort of an odd one because what it will do is it will provide a data frame that gives you a single row of fit statistics for a model. And you're like, well, it doesn't seem like the most useful thing in the world to get one row out for a model. The idea with Glance is you'd feed it a lot of models and you can compare lots of models. If you give it, like 100 models, you can then take this data frame and arrange on different columns and see which one has like the best BIC, the best AIC, the best R squared, you name it, the lowest mean squared error. And then you can filter and figure out what models you want to use in a big set. So it's kind of more of a data science-y type approach thing than common statistics. Okay, so Broom, like every other package, you load it up as library Broom. So as I was saying here, functions like LM, GLM, LME4 functions like LMER, GLMER, all these kinds of things, they produce a list as their output. So if I run an LM or I run summary on an LM, it's going to spit out a list. It's going to look something like this. Text might be a little small. Sorry, I had to cram it all on one slide. So if I run a really simple little linear model here with some play data, if I run summary LM, I get this big printed output that has a whole bunch of random crap in it, right? It has the call, the original function call used to generate it. It has information on the quartiles of the residuals, coefficients. So for instance, this is an estimate for the num1 variable in here. It has a coefficient relating it to my yn outcome of 0.5. It has a standard error. It has a t-value. It has a p-value. It has some fun little stars to let us know it matters. And some other sort of information like degrees of freedom, the R squared, adjusted R squared, F stats, blah, blah, blah. All that general output you kind of want when you're just looking at the console output, okay? A thing about this, though, is that this is coming out as a list. And as we know, if we want to extract things from this, extracting things from lists sucks. You got to remember things like using double brackets, when you can use a quoted versus unquoted like accessing function or syntax, when you can use the $sign and when you can't. This is all kind of annoying stuff. Another problem is that every single statistical function you run produces slightly different output. Okay, so if I take basically the same thing, I'm actually predicting using more or less the same variables. I swap over to a GLM, a generalized linear model function. I fit a binomial model with a link logit. This is a logistic regression or logit model. If I run a summary on this, I get completely different stuff out. I get deviance residuals instead of normal residuals. I look at my coefficients and they look mostly the same, but if I look over here, it has a z value instead of a t value. If I subset this coefficients data frame looking for a t value, like the prior slide, it's not going to find this z value column. It's different, okay? And then the stuff down here is like dispersion information and things like that. So the output between two base R models, which are otherwise very similar, are basically incompatible. You'd have to write completely different code to access the sub-elements of these, even though they're really quite similar looking in their syntax and what they're doing, okay? Well, what Broom does is no matter, for the most part, what you give to Broom, it produces an identical style of output. If I take my LM1 linear regression model and I send it to Tidy, it's going to spit out a tibble, which is a type of data frame, with one row per parameter, and then a bunch of columns with different important pieces of information. For instance, term here contains the different variables that were in that model, including also the intercept. So you've got an intercept, the num1, fac1, fac1. So this is one variable that was a factor with 3 levels. It omits the reference category and then has the 2 other values of the factor in there. It has an estimate. The estimate is like your beta, but this estimate could also be an odds ratio, a log odds, a log count, depending on what type of model you have. It just puts it in an estimate column. It gives you a standard error. And then instead of a t-value or p-value or something like that, it just gives you statistic. The idea here is that whether it's a t-value or p-value, not p-value, but a t-value or a z-value, it doesn't matter. We don't care which statistic it is. We just care it is a test statistic. Okay? And so we have all these test statistics here. So you could compare a GLM and an LM model across similar sort of statistics. It'd be fine. And then it puts out a p-value column. You can also tell it to omit some of these columns or add other ones. There's other stuff you can make it produce, okay? So the nice thing is, if I give this a GLM model, like a logit model instead, I get the exact same output, right? No matter what I feed to tidy, I could put this together into a similar data frame, or I could write one function or something that uses this output from a model like this and does stuff with it, and it would work for any type of model as long as it's supported by Broom's tidy function, okay? This is kind of important because if you do things like generate tables or generate plots and stuff, you kind of want uniform output so you don't have to write a function or write plots that work a little differently for every model in your data, your dissertation, whatever, right? This just lets you sort of put tidy in between the models you run and how you display your output and let it take care of translating that into something useful. And as it turns out, every one of the display functions and packages I'm going to show for tables, plots, all the stuff I'm going to show here in a bit, actually all uses the Broom package to translate those models into usable form so it can plot them or table them. Turns out this is how all the major packages are doing it nowadays. They don't want to write every piece of like the tabling stuff differently for every statistical routine. So instead they let Broom handle it for them. So it's good to know about Broom. Okay. Here's a question. How to know what num1 represents? This is just some play data. So these data, which I'll show a little bit later, I just generated some data that has numeric variables and factor variables. So I can just display sort of random things. It actually doesn't matter what they mean. Fact1 just represents this level of a factor variable. This level of factor variable, num1 is just a numeric variable. Yeah. So example data. Okay. So this is kind of nice. It kind of digests your model results into something you can use. I use this all the time for comparing across models. I'll put them all into like one data frame, sort and slice things. Maybe I'll set up so I have the same like 5 different models and I just extract like, say, the num1 variable and I compare how stable this estimate is across 5 different models. We know how to work with data frames, so you can do all the sorts of clever things that you do with actual data with your model results. Turns out to be pretty powerful. Okay. Another function in Broom is the glance function. Glance just generates fit statistics for your models. It's not the most useful thing in the world if you only run one model, unless you just happen to want these fit stats. So if I say glance, the LM1 linear model I ran earlier, it spits out 12 different fit statistics. If it spits out an R squared, adjusted R squared, sigma is the overall model error, statistic, the p-value of the model, which in this case is probably an F stat, it might be a chi-squared for like a logit model, the degrees of freedom, the log likelihood, AIC, BIC, deviance, the degrees of freedom residual, number of observations, okay? So here's that. What's the rationale to compare t-values and z-values in the same table? They are different things, but asymptotically, they have an identical distribution. Once you get over a relatively small number of observations, they're damn near equivalent. And so it's okay to compare a t-value and a z-value. At small numbers of observations, that's not quite the case, but they're pretty similar. Generally, all you really need to know is that anything that has a value of about 2.0 or higher is what conventional people like to call statistically significant. That's about all I really need to know about T and Z values.
Thank you.
Okay. So glance is like this. The more powerful thing you can use for with glance is to stuff a lot of models in it. And so you could run glance on like, if you ran 100 models simultaneously in kind of more of a machine learning style approach to things, you could then get the fit values for every single one of them and sort through and find the one that's best on whatever metrics you care about. Okay. Another one is augment in Broom. Augment will take the values generated by a model and add them back to the original data. So if I say, take my linear model 1 output and augment the data, what it's going to do, and notice I don't have to return the original data. In R, the linear model object, the output contains the original data also, so I don't have to give it anything else. I can just say augment my model, and now I actually see my original data values for Y, all my predictor variables, but now added to it. So this is the original data frame I fit the model on over here. All this stuff over here is new stuff. These are the fitted values, the residuals for those values, standardized residuals, and then these over here are sort of leverage statistics, okay? Things like Cook's SD, you name it, okay? So this is kind of nice if you want to get these things for your original data. Say you want to use your Cooks SD to find what people might call outliers, right? Maybe you have an assignment in a stats class and you need to remove outliers from a model. You could just augment the model, find the row corresponding to it, filter it out, and rerun the model. Super easy, okay? But you can get these things. I think with the augment, you can also ask for other things or reduce the things given by. Okay, so this is kind of nice. So the real power, in my opinion, of Broom, other than for writing packages, becomes apparent when you run lots and lots of models at the same time. So this is an example of code which you could steal, and this uses a little bit of syntax I haven't shown in this class because it's sort of a little bit more advanced than what's necessary for this class. But what this is, and I'll walk you through it, I'm taking my original example data, and then I am nesting my data by the factor1 variable. Nesting data is a weird thing. What it does is it's going to, you know how if you group by, it kind of splits it into multiple data frames? Nest by does the same thing. It splits your data into data frames by each level of factor. If fact1 takes 3 levels, there's essentially 3 data frames. But what Nest does, instead of just separating them, is Nest collapses each of those down into a single row containing all the data as a list. You're like, why would I want to do that? The answer is so you can do weird stuff like this. I can then say mutate, run a model on all these sub data sets, and then summarize by tidying the output of those models. And what I get as a result here are rows that correspond to the parameter estimates for each of these models for the subgroups of factor. This right here is the model run on the factor where factor takes a value of A. This is a model when it takes a value of B. This is a model when it takes a value of C. Okay, I could then compare, for instance, the effect of my numeric variable across these 3 different models. In this case, they don't look super different. It's about 0.4 here, 0.6 here, 0.6 here. Okay? But you might have a case where they look really different across the models, and that might indicate in a larger model that contains everything, you might want to have an interaction term or something. The nice thing about this syntax like this is no matter how many levels factor1 has, this will run one model for each one of those. If you wanted to run different models for all 50 states in the US or something, you could nest by state, use this exact syntax, and then what you would get out if it was the exact same model, for instance, you would get 150 rows where each pack of 3 of them corresponds to a different state. So this sort of saves you the time of running individual models like submodels on factor variables and stuff. I'd recommend stealing the syntax and playing with it if you're interested in doing that, or sending me an email or a Slack channel message. I'm usually happy to help. Okay, but the powerful thing here is just showing how by doing it with data frames, we can kind of wedge all this stuff together into one thing. It would be really hard to combine list output into a single meaningful object, but data frames can always be squished together because they're sort of rectangular data. Okay. So that's all I got on Broom. Does anybody have any questions about that? Usually don't use Broom directly too often, unless you get kind of into some more advanced stuff.
Do you mind just recapping very briefly what you were doing at the beginning by what were you putting inside different elements of the list?
Different elements of, in this or in?
On this slide, yeah. It sounded like you were, I'm sorry, I had something distract me and I lost about a sentence.
Here, I'll show you what I'm doing. So I can do this with the MT cars data. So I'll take MT cars, nest by cylinder, do MPG by, say, weight and I'm trying to remember what else is in MT cars. Distance? Yeah, displacement will work. Okay. So what this is doing, so the MT cars data set looks like this, right? It's a big data frame with a bunch of different cars with some information on them. Now, if I take MT cars and say, group by, say, cylinder, and I run it, oh, I gotta load my tidyverse here. I want that too. Okay. So if I group on cylinder, nothing different actually happens. So it doesn't change my data in any way. Group by just changes how later things work. This is not true for nest. If I say nest by cylinder, this is my new output. This column is by levels of cylinder. So cylinder 4, cylinder 6, cylinder 8. This over here has compressed all remaining columns of the data frame into a data frame nested inside of this cell of the table. This is something referred to as a list column and is the way SF data frames we saw last week work. They nest a whole bunch of information into a single cell so that you can do fancy things with them. In this case, the fancy thing we're doing is running a model on each of these cells individually. By saying mutate model equals list LM this, but the data equals data, what this is actually telling mutate to do is to go unpack each one of these data frames one by one, run this linear model on it, and assign its output to a new model column in our data frame. If I run it, we're going to see this. A new model column is created, which is itself, again, a list column with some weird nested data. I can then summarize it to unpack this model data frame using tidy. If I do that, now we end up with the unpacked results from those tidy models. This is very complex and is sort of difficult to sort of explain. But this is sort of how you can do complicated things with like model objects inside of a data frame context. It's well beyond what I teach in my class because it involves list columns, weirdness, and stuff that's a little hard to explain. If I taught an advanced R class, this is one of the things I'd cover like in the first week or two.
This is awesome, thanks. It sounds very similar to the epi modeling work I did this year.
So here's some questions here. Is NestSpy related to hierarchical linear models or multi-level models for the next one? Not exactly. So what's going on here is it's actually fitting 3 completely separate models. If you were doing a multi-level or hierarchical modeling framework, if you wanted to get different coefficient estimates for each level of cylinder, you would fit a multi-level model with random slopes. Is what that would be. And that would actually be a way better way to do this than running separate models. In fact, in almost all cases, running separate models is just a waste of your statistical power. But it's a little easier to explain to people than hierarchical modeling with random intercepts and slopes. So this is perfectly fine to do. Often the results will be very similar. I mostly do a lot of like HLM in my stuff, but sometimes I'll do stuff this way too if I just want to take a quick glance at things.
So they are different things, yeah, right?
So what?
I mean, they are different things.
Yeah, but the results could be often very similar. Yeah.
Sorry, can you explain what is the group's job in the summarize line?
Oh, that's an excellent question. So if I don't put that there, it will stay grouped by cylinder. And so it'll say regrouping by cylinder override groups. I actually just put that there because I didn't want to see the error message, this thing pop up in my slides.
Thank you.
Yeah. Good eye. Okay. But yeah, this is a way to automatically drop groups after a summarize so something stays grouped too. Okay. Anyway, continuing on. So let's plot some model results. So we've used the ggplot function or layer geom_smooth in a lot of past examples throughout this class. geom_smooth generates what are called smoothed conditional means. This includes things like low S curves and generalized additive models or GAMs. Okay, so those are those nice kind of bendy lines going through our data. The thing is, though, is that things like normal regression models, linear regression models, logit models, all of these things are themselves conditional mean models. Ordinarily, squares and GLMs are all types of conditional mean models, like a low S or a GAM model. They just make different assumptions about the parameters. We can actually use geom_smooth to depict these common bivariate models. We can run a standard linear regression or a logit model, even polynomial regressions, okay? I'm gonna show you this just using Gapminder data, which we're all familiar with from week 2 and homework 2. So this is sort of a conventional use of geom_smooth like what I've shown earlier in the class. I say here, I wanna make a ggplot using the Gapminder data. My aesthetic is going to be x-axis year, y-axis is life expectancy. I want to color my observations by continent, which as it turns out implicitly groups my data also. I say I want points for all the observations in the data. I jitter them slightly so you can kind of see where they're at. And then I run a geom smooth. Now what you see here is that the geom smooth here generates a kind of a nice smooth line that allows it to curve through all the observations, right? This is a normal geom smooth we've used in the class. So by default, geom smooth, if there's less than 1,000 observations, it will fit a low S smoother, which is a type of local polynomial regression. It's a non-parametric method for drawing conditional means. If you have more observations, it'll fit what's called a generalized additive model, which is a type of spline model. They look and they function identically. It's just GAM models are computationally easier to calculate. So with a lot of observations, you want to run a GAM. Okay. The nature of these things doesn't matter. These lines are just one way to approximate the average at each year for each one of these continents. Okay, that's all that matters. But these things sort of just arbitrarily bend however they want. We might say instead, what we want to do is force these lines to be straight lines. Well, as it turns out, a generalized linear model or standard linear model is a straight line drawn through your data. If you want to make a straight line drawn through a bunch of stuff, you use a linear model, okay? So I say geom smooth, but now I give it some arguments. I'm saying here, I want it to calculate a generalized linear model, a GLM model, with a formula of y tilde x. This just says the y variable life expectancy is dependent on the x variable year. This is the exact same sort of conditional mean relationship as before, but because it's a GLM model, the line has to be straight. Okay? That's all that's happening here. If you want a wiggly line, you don't use a standard linear model. You could use a LOES or something. If you want a straight line, you use a linear model. It's the definition of the model, right? It draws a straight line through your data, or at least through a transformation of your data. Okay? So this is literally, this is the regression line. If you manually calculated the regression line using a linear model, created some data and applied it to your ggplot, you would get the exact same line. You would in fact also get the exact same confidence interval around the line if you calculated it properly. So this saves you some time. Okay, the thing is, you can actually dress these models up. Maybe you do believe that you want a curvy line through your data, but you want it to be a parametric curvy line. That is, you might want to define it as a quadratic model. As it turns out, ggplot can take all the same formula arguments you would put into a normal LM or GLM function call. So I have the exact same method equals GLM, but I've changed my formula. I'm now saying y is dependent on some quadratic function of x. This is one syntax way you could say, basically this is x plus x squared in your model. This is technically this is an orthogonal polynomial. It'll give you the exact same predictions, but gives you uncorrelated results. Yeah, so this draws a nice quadratic curve through your data. It's a little less flexible than like a low S smoother. It's parametric and you can get those useful estimates out as if most people are capable of directly interpreting a quadratic's parameters. I knew an economist once who really could draw the line by reading the parameters quite nicely, but that's the only person I've seen do that. Because economists are robots. Okay, so you can do things like that. The thing is though, you might want to run more complex models than this. If you want to run anything other than a bivariate model, you're gonna be in trouble. The thing is, your ggplot is a two-dimensional model, right? Your 2 dimensions here. You got a y-axis and an x-axis. If you want to add a third model, a third variable here would force you to draw a hyperplane of some kind or a plane through your data. You can't do that in 2 dimensions nicely. This means if you want to do a more complex model, you can't just feed it straight into a ggplot. It's also hard to do things like complicated models like nonlinear probability models or multi-level models. It doesn't do those nicely inside ggplot. So we need to move beyond this geom smooth function, okay? So before we can do that, I want to introduce you to a little bit of vocabulary. Some of you are probably familiar with this vocabulary. If not, this is going to be a rapid introduction to the idea of counterfactuals, okay? So the idea is that we're often interested in what might happen if some variables in our data take particular values. Sometimes these are values not seen in the actual data, okay? This is basically, what would we get as a result if we changed x to be 5? That kind of thing, while holding everything else constant. This is a thing we want to know all the time, right? Well, when we set variables to be certain values, we refer to the values we set as counterfactual values or just counterfactuals. This is very common statistical language. Okay? A counterfactual value is just some kind of hypothetical value for a variable. So if we don't know anything about a new observation in our data, we might predict that its value, its estimate is going to be equal to the result given all the other variables are at their mean, right? This is why if you don't know anything else about what's going to happen, you would just guess, set all your variables to their average values and use that to predict an expected outcome. Okay, that's a type of counterfactual. What would be the most average imaginable case? What would be its expected outcome? Okay. Other times, though, we may have very, very specific questions that require setting lots of combinations of variables to particular values and then making an estimate or prediction. You might ask a question like, well, what would be the life expectancy specifically in the United States if we dropped the GDP per capita 20% using our Gapminder data? So that's setting country to be United States, and that's setting GDP per capita to be 20% below its current value. Maybe we're projecting it forward a couple of years or something. These are counterfactual values. We're saying we want to set our data to these values, which don't exist in our actual data, and then predict values with them. Okay? So providing specific estimates conditional on the values of your covariates is a really nice way to summarize some results. This is especially the case for models that have unintuitive parameters. Instead of giving people log odds or odds ratios, both of which are very difficult to interpret, and I will say as an aside, if anyone ever tells you it's very easy to interpret log odds ratios, that person is either doesn't know they're wrong or they're lying to you. The only case odds ratios are easy to interpret is with very, very rare outcomes. So they work pretty well for disease stuff. Other things, odds ratios probably do not mean what people tell you that they mean. If you have an odds ratio of 2, it does not mean that thing is twice as likely to occur. It means the odds are twice as high. And that means a very different thing depending on how likely that outcome is. Okay? Giving people log odds or odds ratios as a result doesn't help them, and in fact often misleads them. For something like a logit model, it's much better to give them something like a probability difference. So instead of saying something like, well, the odds ratio is 2.4, no. Instead, you might say, if we go from a value of 0 to 1 on my variable, if everything else is held at its mean, it increases the probability by 0.25. Then you're speaking in terms of probabilities. People tend to get probabilities pretty well. It's 25% more likely to happen. Okay? Counterfactuals enable us to do that sort of thing with models like logit models. Okay. So normally calculating counterfactuals is a gigantic pain. If you've taken, for instance, maximum likelihood estimation by Chris Adolph, you might find calculating counterfactuals in that class can be quite a challenge, requiring a lot of code. So it turns out it's really, really, really easy to do using a different package called ggfx that I evangelize to people all of the time. It's not quite as powerful as the approach you'd learn in maximum likelihood, but it works in most cases that people want to do. So if we want to work with more complex models than we can fit into ggplot, we can use the ggfx package to create and plot tidy marginal effects of our models. That is, these are data frames that have ranges of predicted values that you can send to ggplot to plot the model results. I'm going to focus on 2 functions today in ggfx, while there are a bunch more. The main ones I use are ggpredict. This computes predicted values from a model for some outcome variable at the margins of specific variables. That is, you could set a variable to a bunch of different values or a range of values and get predicted levels of the outcome, holding everything else at whatever values you want. This is pretty nice. You can hold everything that's mean, but you could also hold them at their modes or hold them at low levels or high levels. Okay. The next one is a plot.ggfx method. If you take the result of ggpredict and send it directly to the plot function, it makes pretty ggplots. As I'll show in a minute, this makes your life a lot easier. This package, ggfx, you can just do install.packages ggfx, and you got it, and you can work with it. Let's see how it works. So to show this off, I use some simulated data. So these are, I think, actually the same data I was using earlier. So I just swapped the order of these slides. This is just a data frame with some known relationships between a bunch of categorical and numeric variables. This doesn't actually matter, but if you want to generate a test data set of your own like this shows you how I did it. Okay, steal this code if you want it to do some simulation. It doesn't actually matter. Okay, so the idea with ggpredict is ggpredict will take a model you fit and produce as a result a data frame with one row for every unique value of a supplied predictor, or for continuous variables, one row for sort of evenly spaced values of the predictor variable. Okay, this variable or variables will be defined by the term argument. Each row will then contain an expected or estimated value for the outcome plus some confidence intervals. It works like this. So if I run a standard linear model, again, this is actually the same linear model from before, but I'm refitting to show you. This is an LM on some numeric y variable predicted by a numeric variable and a factor using my example data from the last slide. I say my estimates from my linear model, I'm going to assign to that the result of ggpredict, my linear model, the terms equals num1. So this is saying I want predicted values from my model across a range of values for my numeric variable. Okay, that's the only arguments I got to give it. This is what it's going to produce as a result. This is actually a nice display of it. It's actually a normal data frame, but they display it this way for to make it look pretty. So if I take my LM1 estimates object, it says these are predicted values of yn, my outcome variable, x equals my num1 variable. These are values of my num1 variable. It begins at the lowest value, or approximately the lowest even integer value it saw in the data, goes up to the highest value it saw. At each of these levels of x, this is the predicted value of y, and this is the 95% confidence interval of that prediction. Okay, and notice here it says this result is adjusted for my factor variable being set to its reference level. So these results are all across all values of x, or the full range of them, while holding constant other variables in the model. So this is just going to be, if we could hold constant this factor, this is what we would expect to happen for our outcome variable across the entire range of valid values of x. In this case, num1 is x. You're like, okay, this is kind of nice. This is something that might be useful in a homework assignment or something like that. But how does this get me closer to displaying something nicely? Well, it turns out if you feed that data frame straight into the plot function, it will plot those results as a ggplot. So ggfx includes what is called a method for the plot function called plot.ggfx. If you send the output of a ggfx call to the plot function, it produces a full plot of the marginal effects. So this is num1 variable on the x-axis, my y outcome on the y-axis, the predicted values of yn given each level of num1 with a nice confidence interval around it, calculated using the appropriate method. So I think by default, this uses a likelihood profile method for calculating the confidence interval, which is the correct way to do a confidence interval across a counterfactual value. Okay, so you can do that actually if you use a pipe one line of code to get nice marginal outputs like this that convey sort of how a variable works across a range of values better than any table. So whenever possible, writing an article, do plots like this and do the table. And then if they tell you to cut the page count down, insist on moving the table into an appendix or cutting it out and keep the pretty graphics in. It's generally the way to do it. Some journals really insist on the tables and putting the graphics in the appendix, or even worse, make it so all the graphics are at the end of the article and there's like a reference saying, find figure 1 here, which is stupid nowadays, but you know, what can we do? Journals still live in the 70s. Okay, so ggfx and ggpredict are actually, so this is a question. Why use plot instead of plot.ggfx? Well, the thing is if I say plot and the object I give it is a ggfx object that is the result of ggpredict, it's actually running plot.ggfx. This is something called, as a result of object-oriented programming. It runs a different function for plot for every object you give to plot. You've probably never noticed it doing that in the past, but if you think about it hard, you'll probably remember times when you gave some object a plot and it produced one type of plot, and you gave a different object to it and it gave you a way different plot. It turns out it's running a different function for everything you give to plot. And R works this way in all cases. You just don't notice it too much. It's kind of runs in the background. So here you just use plot, but it's actually running plot.ggfx. And if you want to know how plot.ggfx works, you're going to want to run $plot.ggfx, not $plot. Okay? It's one of these things I kind of hide from people in the class because it starts to blow your brain up.
Did Chuck freeze for anybody else?
Yeah, I think so.
Yeah, during
Yeah.
the lab yesterday, his I think his network card sort of tanked. So
Oh,
I think
okay.
he's coming back. It's just overheating, and he should be back.
Yeah.
Thought he was focusing really hard on the question in the chat.
Yeah, I did too.
I know, I thought that too, and I was like, it was a pretty straightforward question.
And then it went just a little too long. Yeah, yeah, there he went.
Well, maybe, I don't know, maybe someone else can answer this, but how does this predict seem different than just doing like a simple linear regression on a variable in your data? That seems like what he's doing, but I'm like, maybe I'm missing something.
I don't do simple linear regressions give you the confidence bounds.
Oh, yeah. Yeah, that might.
I don't know. I should let him answer it. I just remember that like when I was in biostats, they had to do some pretty fancy footwork to get base R to do confidence bounds.
Mm,
It ended up requiring a lot of extra code to
okay.
get it, if I remember right, but it's also been about a year, so. Hey, as long as we're here and the class is pretty small, can I just like throw out like a getting to know you question? Like, I'm curious to know what people have been watching while they're stuck at home. I feel like I'm kind of stuck in a rut watching what I've been watching on Netflix. Like, has anybody found anything really cool to watch?
Oh man, I'm watching Fargo.
Oh yeah?
It's so good. And I lived in Minnesota for the past 9 years, and I was like, wow, you guys got the accent like spot on. But
Nice.
it's really good. But that's on Hulu. It's not on Netflix.
Okay. Did you watch the original Fargo before watching the series?
Yeah, it's like semi-related. But in Fargo, every season they're all kind of related, but like pretty different casts and storylines. So
Okay,
so yeah, it's like somewhat related to the original movie.
nice.
I'm watching The Undoing right now. So if you've seen it, please don't say anything because I'm just about to finish it, but it's been good.
I saw that. I keep like wanting to dig into it.
Yeah,
Never heard
it's
of
good.
it.
I think it might be HBO. I don't know. I just download everything. So
It's kind of old at this point, but Chernobyl, if you haven't seen that, was really like I couldn't stop watching it. I know there's some like historical inaccuracies, but overall, I think it was a pretty interesting story.
Okay.
that
I think
I
it's
second that.
actually
That was incredible, and I binged it. I think that was the first thing I binged in quarantine. Actually, it's so good.
Is it on Netflix?
I think it's on HBO.
Okay.
Man, it looks like it
But
might be time.
again, I downloaded that or streamed it or something.
That's how I generally get my sports games.
Yeah, I'm generally trying not to watch too much TV, but it's there's no leisure reading happening, obviously, while in school.
Yeah, I've got this like one book on my nightstand that I've been trying to read basically since the semester began. Um, I think I'm halfway through. Like it's pretty poor. Do you think you'll ever read again for pleasure after grad school, or do you think it's going to kill it for you?
I don't know. I think there's just more reading to come in a postdoc. So I'm like, shit.
Yeah.
I still read a ton, but it's because it's a habit. But for me, it makes the academic reading. It's like the only way I get through academic reading is because I take a break and I read. Like I'm always reading some really stupid novel that so that you can like have some like really light reading like every day.
Yeah. I think maybe that was my downfall. I was trying to read like a book that was slightly too serious on the side, and it should be like bubblegum, not bubblegum, but like just not super hard, right?
Yeah. In the summer, it's so enjoyable. I think I read like 4 books this summer.
Oh, that's great. Like I miss commuting to school on the bus because then it's like, oh, I've always just got my like slim little thing to read, and that's like I'll slowly work through a few books during a quarter, and yeah. And it's a way to force myself to like not pull out my laptop and try to get a little more work done on the bus. Like, no, just let it go.
Yeah, definitely
like
podcasts and books.
Yeah.
I also miss my commute on a train. It was probably when I did all my reading. But I actually have my Kindle right here. Sometimes if I have like only these like weird 20-minute breaks between classes, which I have several of those in the week, I won't get anything done anyway, so I just read. But it
Yeah.
is all about having an easy book.
Yeah.
Dang, we really lost him.
He replied to the Slack and said
Oh,
his home internet went down, just getting it back up. Yay!
Yeah.
we were
Yeah, home
talking
internet
about
down,
Netflix.
I'm now tethered to my cell phone. So
Dude,
this should work. Okay, let me fire this up.
should we turn our videos off? Like, will that help this run smoothly, or does it matter?
Oh no, my phone is very fast. Not worried about it. Let's see. Is my video coming through fine?
Yep.
Yeah.
Yeah, pretty sure my phone is like pulls down not much worse than my home internet. Okay, let's see. Share screen, screen one. Okay, just like nothing happened. Actually, I thought it was my computer. And then I looked at, oh my God, why can't my phone connect to the Wi-Fi? I turned off and I'm like, okay.
Sorry, Chuck.
Everything looked fine on everybody else's end?
Did you see my question right before you cut out?
Oh, no.
I was just wondering, like, I don't really get what the difference is between this predict and doing like a simple linear regression on one of your variables. Is it just that you also get the confidence interval?
Well, you'll get the confidence interval, and it's also, well, are you saying a simple linear, like two variables?
Yeah.
Well, in this case, this is actually also controlling for other variables. So it's actually, this is a multivariate variable regression.
Okay.
If that makes sense, yeah.
Yeah.
Audio is a little garbled here. Let me see. Can't even guarantee that's from. How's it now? Same. Okay. Yeah, that might just be a bandwidth issue. And there's literally no way for me to deal with that. So let's turn that down to low quality. Okay, well, we'll just have to make do, unfortunately. Okay, unless my home internet comes back up, and then that'll be fun. Oh, okay, yeah. Neat thing with GG effects, though, is that, oh, now it's choppy too. Okay.
It's okay.
1 second, I'm going to see if my home. Okay, I'm going to try something really fast. Let me. See if this works. It's not doing anything. Okay. This doesn't make any sense. Am I coming through still?
Yep. Yeah, you're pretty clear now.
Yeah, that's very strange. I don't know what's happening. So, okay, I'm gonna keep going then. Something with GG effects is that GG effects can take multiple variables as an input to the GG predict function. So here's an example where I've taken a generalized linear model with a binary outcome, a whole bunch of predictor variables. You can tell it's a logit model because it says binomial link equals logit. I can pipe it directly into GG predict like this, and then I can give it multiple variables. Here I'm saying I want predictions over my numeric num1 variable and my factor fac1 variable, and then I can plot my results. What I see here is the red line corresponds to factor level A, factor level B is blue, factor level C is in green. These are predicted probabilities. This is kind of nice. So with a logit model, you send it in here, instead of getting log odds or odds ratios, you get the actual predicted probabilities at different levels of the variables you give to it, as many variables as you want, basically. I think it supports up to 4 right now. But this is kind of hard to read over here because they're overlaying each other. The neat thing with ggfx is that if you change an argument in plot to be facet equals true, it will split your factor variables into multiple facets in your plot. So now I have one plot for factor level A, one for B, one for C, so I can compare across all of these different levels of the factor variable. Oh, and of course, the cat comes in to visit too. It's going to be one of those lectures. It's got to be the last one, right? Okay. Yeah, so it goes. Yeah, come on. Why not? Okay. So anyway, we can now facet our plot out to multiple facets like this. This is something really powerful and would be a huge pain to do in other cases. We'd have to predict a whole bunch of predicted values for a whole bunch of different variables. We can just send it straight to plot. It takes care of figuring out how to make them nice. Okay. Other things we can do with ggfx are set actual values of things to see how these plots would look at set values. This is the same logit model I ran before, but now I say ggpredict terms equals my num1 variable, but I want it to range from -1 to 0 to +1. So the square brackets here let me set specific values of this variable. Fact1 is just going to be displayed as level A and level B. If I then plot it, what we see is only level A and level B of the factor are displayed, and my numeric 1 variable runs from -1 to 0 to 1. So this lets us set specific values we want and then generate counterfactual plots. This is kind of handy, pretty powerful. You can also have it calculate numbers for you. For instance, you could say num1 mean SD, and this is going to calculate predicted values at the mean and then -1 and +1, one standard deviation. You could also do min max, which would plot the minimum and maximum values of a variable. So it has some sort of flexible little things you can put in brackets to get kind of the exact things you want displayed on your plot. Okay, it's got a lot of options. It's a huge package, so you can kind of look into them and see other things. Okay, another thing is that if you give categorical variables to ggpredict, it knows they're categorical variables and it changes the type of plot to correspond to that. In this case, I've run a standard linear model, y is an outcome being predicted by 2 factors. If I say ggpredict and my terms are my 2 factors, and I send it to plot, it doesn't do line plots because line plots don't make sense for categorical predictors. So it converts it to being dot plots. For instance, this right here is the predicted value of y, given factor 1 is A and factor 2 is yes. So these are predicted values at all those specific categorical levels. Okay? Come on, cat. Oh, you're unhappy. Fine, be that way. She's like, pet me, but please pet me only in my box. So I tried to pick her up. She's like, no, I hate you. And then she runs out. It's one of these days, right? And now she's going to go yell outside, so I got to close the door. I adore my cat, but that is her personality. Okay. So, continuing on, this is the best lecture yet, right? We saved this all for the end. Chaos. Chaos reigns. Okay. So, some last notes on ggfx. There's a lot more to this package. This is a huge package. I recommend it all the time. I use it myself all the time. It has great documentation. You can run through. It can do this for just about every imaginable type of model, has tons of options, works with everything. Okay. Other things I didn't cover now that it can do, for instance, is predicted values for your polynomial or interaction terms. It's really hard to explain in a table interaction effects in models, but it's really easy to plot them, and ggfx makes it just cake. Okay? Works with lots of packages. And the cool thing is, if you look back at these plots, as you can tell by the appearance, these are ggplots, which means you can just do a plus at the end of this and add any layers you want to them. So you can modify them with everything else we've learned in the class. It's just a ggplot, do what you want with it. Okay. If you want to do something more complex than what ggfx can let you do, I do have some slides that are, it's actually code taken from a journal article of mine a while back on doing really complicated counterfactuals manually using a combination of dplyr syntax and simulated draws from multivariate normal distributions. If you need to do something really crazy, steal my code to do it. Maybe put me in the notes or something, or in a citation somewhere. Okay. So now we're going to move on to making tables. Okay. So we've used up to this point the Pander package for making crappy, ugly tables in our Markdown documents because it's really simple and easy to use. Okay. Pander works on just about all the common models we encounter, but it also works on little tables, data frames, things like that. So it's really convenient, right? Works across all the common stuff we encounter. So we can do things like this. We can say, I want to run a Pander on my linear model 1 object, and it's going to spit out a nice markdown based table. It shows intercept, weight, horsepower, this basically looks like if you ran summary on LM1, this is what you'd get for that coefficients block. It's basically how it actually extracts it, right? It's going to put a caption on it. It's a pretty simple table. If you need a little bit more information, you could run pander on the summary of that linear regression model. It's going to spit out the observations, standard error, R-squared, stuff like that. Okay, so you can, if this is all you want, run pander on your linear models and get some basic tabular output. Okay, so this is great for basic R markdown documents, memos, maybe things you send to your advisor or something like that, but they are never basically going to be publication ready. So if you want to make more publication ready, or at least pretty tables for other things, I'm going to introduce one big package and two sort of small packages for making nicer tables. There's a lot of table making packages out there in R. There's some I really like that I'm not going to cover today too much, like Cable Extra is really good, Flex Table is really nice, but today I'm just going to cover mainly GT, which is a package from RStudio that kind of integrates nicely with a tidyverse for general table construction, and then model summary and GT summary for specific types of summaries. Okay, so the GT package is really powerful. If you need high customizability for your tabular output for either models or displaying your data, descriptive statistics, all that kind of stuff, GT is really good. You can make just about anything you want. I'm going to do an example here using the Star Wars data frame that's built into dplyr. So one of my favorite things about the dplyr package is it has this incredible list data of Star Wars characters. And so I'm going to use that today as my example for tabular output. This is just some quick data cleaning I'm doing here. It's a complex data frame, so I want it unnested into a nice format. And I'm also correcting the fact that Obi-Wan Kenobi is listed as having his Jedi Starfighter in episode 1 or episode 4, which is clearly incorrect. That's an episode 2 thing. Okay. So anyway, this data frame, once cleaned up, looks something like this. Basically, I have a character's name, species, the starships they're associated with, their character's mass and height, and I want to tabulate this nicely. And there's a question in chat over here. Is facet over grouping terms related to reference categories? Kind of. So the reference category is used in fitting the model, but once you plot it in ggpredict, it's going to make that reference category one of the facets if it's a term you include. So you don't like drop it out. This is also another nice thing. If you do a regression model that has a reference category on like a series of dummies, usually you just have to omit one of those from your table. It makes sense. It's a necessity of omitting it. But if you do graphical results, you can actually display its own subplot for that particular category, so it doesn't look like it just doesn't exist as having been absorbed by your intercept, if that makes sense. Okay. So here is a very basic GT package. So if you load up library GT, you can just take a data frame like TES characters and send it to GT, and it's going to produce a simple markdown tabular output. So because GT only works with data frames, if you wanted to work with model results, you'd send them to tidy and then send them to GT. That is tidy in the Broom package, and then you could produce them. So this is a basic GT package, or GT package plot or table. GT just renders that data frame as a plain markdown thing, kind of looks like a table generated by Panda or something, right? Okay. So we can add on to this and modify it using both a combination of dplyr stuff and GT stuff. So I started with this table here. If I use group by on the data going into the table, GT recognizes grouped data from dplyr. So I've said, take my characters, group them by their starship, and display the GT table. Now this is broken up into subtables. This table is characters, it's an image. This table is characters associated with an X-Wing, characters associated with no ship, with the TIE Advanced, with the Millennium Falcon, with Slave One, right? You know your Star Wars, these are generally correct associations, okay? This is kind of neat. So you can just say group in dplyr, send it here, and it recognizes it. It plays nice with tidyverse style functions. Yeah. Next thing, we might want to make it so that we remove, for instance, the row name for the categories. So by default, name here, right here, X-Wing, Luke Skywalker, Wedge Antilles, whatever. What I'm going to do is say that name column is a row column. Can we hear the children outside screaming? This is perfect. This is my best lecture ever. I'm
Just a little bit. It's faint.
so good. Okay, so if we have one column in our data frame that is essentially row names for our data, we can specify in GT row name column, in this case, equals the name column. So you saw before the name column. By specifying it as a row name, it drops the column name and then indents and separates the values of the row names to signify these are not things associated with a measure, but rather this is an identifier for each of the unique observations in our table. This is a way to make our table look a little pretty. See, it adds a dividing line here, okay, and indents them slightly. So we started to dress this up a bit. Next thing, I might want to modify the header at the top. Add a title and a subtitle to it. So I say tab header, the title is Star Wars characters, and the subtitle is In the Empire Strikes Back. You can see before the header, with the header. The table's otherwise the same, but tab header adds a nice title bar to it. The next thing I want to do is I want to add a spanner. So the idea here is that I think mass and height are closely associated variables, so I want to put them in their own little group, but leave species alone. So I can say here, tab spanner. The label for this spanner is vitals, which is the text that goes above it, and it's going to span two columns. It's going to span mass and height. This draws a little line over mass and height, groups them together, and puts one title over the top of them. So if you have a bunch of variables that are sort of go together as a cluster, you can mark them off like this and put a spanner above them. This is also the way you would do it if you had multiple models in one table and you had like these columns are one model, these columns are another one. You could mark them off and put a spanner over model 1 and model 2, right? Okay. Another thing I might want to do, and you'll notice here, as I said, GT works in a tidyverse sort of fashion. So I'm just piping table making functions together, and it just modifies it as we go the way dplyr works. So this works basically how we've seen data manipulation so far. But yeah, so here's a question. How much text formatting can you do, like creating bold text for the group category? The answer is you can do basically everything you could ever want to do. This is very flexible. I'm going to show actually, I don't know if I bold, but I do mess with some fonts or something in a minute. Okay. So the next thing I want to do is, these are raw variable names up here, species, mass, and height. I'd like to dress them up a little bit in my table without having to edit my data. So I say here, let's change the column labels. I want the mass variable to be displayed as mass in kilos, height as height in centimeters, and species I just want capitalized. This leaves the variables in the data the same, but modifies the actual displayed values of them. So now species, mass kilogram, height in centimeters. Next thing I want to do, I want to change the formatting of cells in the table. So you'll see here, these are like 77.0s and all that. Notice how the decimal place basically doesn't matter for any of these people except Boba Fett for some reason needs an extra decimal of precision in his weight. Okay, this is unnecessary. So I'm going to say, let's just cut it out. Let's reformat this number. So I say, format the numbers. Which numbers? Columns, the mass column. Notice you have to specify var's mass. It's a sort of a tidyverse style syntax with selection functions. Anyway, select mass here. Decimal 0 says I don't want any decimal places in my numeric values. It chops off all the decimals and otherwise leaves the numbers alone. Format number can do all sorts of additional formatting, and there's format functions for many other things. Format character, you can format specific cells to do things like italics and bolds and all that, even colors, right? Okay. Next thing I want to do is I don't like the alignment. So this is left aligned here. This is like right or center aligned. I'm going to mess with my column alignments. This is something you can't do in Markdown at all. So some people have asked me questions about how do I like center or left justify things in a Pander table. The answer is you can't. Markdown actually doesn't support text alignment at all. GT generates its tables either using LaTeX or using HTML. This is an HTML table over here, which supports alignment of text. So I say here, I'd like to align some columns. How would I like to align them? Center. Which columns? Species, mass, and height. So now the species, mass, and height columns are centered in their respective columns, but these ones are still left justified. So yeah, so here, if you had a large table, could you select var all? You'd actually say var, I'm trying to remember if it's everything. I think it's everything, parentheses. This here actually takes dplyr select functions. So you could do starts with, ends with, matches, and all that, and it will do them. So I think it's everything, parentheses, would get every column. Okay, one last thing I want to do. I could reorder all of the column groups in here. So a group is something like X-Wing, No Ship, TIE Advanced. I say I want the X-Wing and the Millennium Falcon to come first. So I'm going to say here, row group order should be groups, X-Wing, and Millennium Falcon. Kind of like the factor releveling functions in ForCats. You just can name specific ones, in this case, X-Wing and Millennium Falcon. It moves these to the front and leaves everything else in the same order. So here, X-Wing and Millennium Falcon are jumped to the front. The other ones are just left in their original order. Okay, so here's a question. Can we use GT to edit variable names in a regression results table? Sometimes variable names are used to read. Yes, that's actually exactly what I was basically doing here. So things with like changing the labels of the columns and things, you can edit them just like that. And in fact, I think I'm going to show in a bit how to do it using the model summary or GT summary packages. But yeah, you can absolutely change it. And that's the way I do it. I usually leave the variables in a clean name, and then the tables display them differently using a reference in the GT or whatever package call. Yeah, massive flexibility. Okay, so this was our original table on the left. This is our cleaned up one on the right. So this one, using purely R syntax, no manual thing, not dragging into Word or anything, can produce quite nice looking tables ready for like a memo or even ready for a published paper, okay, without having to dress them up. Kind of cool. Okay, so caveat to GT. GT is a relatively new package. Its 1.0 version hasn't even come out yet, and producing PDF output with GT is a little unstable right now. That's one of their things. They want to stabilize the package, then make its LaTeX output nice. If you need to produce PDF output, you need good LaTeX tabling. Okay, so if you want to produce nice LaTeX tables in your PDF documents, I recommend using Cable Extra, or I don't really recommend, but I at least mention it, the Stargazer package, okay? So like GT, Cable Extra allows construction of tables using a dplyr style piping syntax. The difference is Cable Extra puts out nice LaTeX tables. It's a little less flexible in some ways than GT, so I prefer GT most of the time, but Cable Extra is very powerful also. Stargazer also produces nicely formatted LaTeX tables, but Stargazer is very idiosyncratic and very dated in its style. It doesn't support a lot of new models, and sometimes you just cannot customize important things. The reason for that is it's not built on top of Broom, and it doesn't work with data frames the way like Cable Extra and GT do. So its flexibility, Stargazer literally has a different method for every statistical routine you send to it. This is a very dated approach, and so it's kind of inflexible. Also, the author doesn't even have a nice GitHub repo, so if there's errors in it, you can't submit fixes for them. So sometimes the authors just don't fix important errors in like the package. This is very, very annoying. Okay. Anyway, if you want to edit LaTeX documents or work directly with LaTeX, you can do that in R using Sweave documents, which are .rnw files. You might also instead want to work in a dedicated LaTeX editor. If you're going to do that, I recommend actually not using a LaTeX editor on your computer at all, but instead using something like Overleaf, which is an online LaTeX editor that takes care of the hard maintenance of a LaTeX distribution for you. Okay. My true strong recommendation is to just not learn and use LaTeX and instead use better, more modern things, because LaTeX will destroy your life. But if you really must use it, do something like that. Okay. So our Markdown, though, can do most basic LaTeX syntax, things like displaying equations and stuff. So most of the time, you're okay without going to an RNW file. Okay. Anyway. So another package for generating tables is Model Summary. Model Summary combines the Broom package with GT and Cable Extra to produce tabular model summaries of most common models you could fit in R. In fact, basically anything generated by Broom works in Model Summary. The advantage of the model summary package is because it can switch between using GT and Cable Extra, it can produce nice tables in HTML, Markdown, LaTeX, raw text, image, and Word documents simultaneously. So it does just about anything you want. It just sort of works. This is kind of nice. Okay? The key function in model summary is the mSummary or model summary function, which will create summary tables of models you give it. You can then add on to it using either GT or Cable Extra functions, depending on the output you pick. So model summary works like this. So if I fit some type of model like this, LM, MPG, weight using the MT-CARS dataset, I could say model summary of this model object. Okay? It's going to spit out a really basic looking table like this. By default, it's going to have the parameter estimates, the number of observations, and a bunch of fit statistics. Okay? This actually looks a lot like a Pander table. The reason for it is by default, model summary is using Markdown, just raw Markdown. Markdown is very simple. It works nicely, but it just kind of generates a bland looking thing depending on the theme you have in your Markdown document. Okay. A neat thing about model summary, though, is model summary can do multiple models simultaneously, and it knows how to assemble them into a proper table. So if I fit 3 models, I'm going to call them model 1, 2, and 3, with different variables on the same data set, I can put them into a list. Model list is a list of these 3 models. I can then run model summary on this list object that contains 3 models, and it produces a full table showing model 1, model 2, and model 3 in the order they're provided. So this allows you to produce that really common style table we've all seen in journal articles, where somebody starts with a naive model that makes no sense and conveys no useful information, and slowly builds variables one at a time until it gets to their preferred specification as a way to justify their specification by saying these are all dumb models. This is a thing people shouldn't actually do in papers, but it's a common stylistic thing in many disciplines. So you too can do it with model summary very easily. Okay. Yeah. Okay. So a nice thing about model summary is you can change its output type. So for instance, you could say mSummary, take that list of models and change the output to a LaTeX output for a PDF document. This is the exact same table from the prior slide, generated as LaTeX output instead. You'll notice this already looks a lot like journal article tables often do, because they usually do their typesetting in LaTeX. Okay? So in your PDF document, it would show up looking like this. Okay? So this is nice. You don't have to do any weird juggling, mess with LaTeX. You just say, nah, make it a LaTeX table, and it spits it out. Okay. There's a lot of customizability to the model summary package. I'd recommend going to its documentation. It's a big package that can do a lot of stuff. If you want to change fit statistics, how things are displayed, any of that kind of stuff, go and mess with it there. I'm not really going to delve into it, but check it out. It's a powerful package. Okay. If you want to save output from model summary, you just say something like model summary, the object you want to generate the summary of, and then output equals some object. Depending on what object type you give, in this case I did .png, it figures out how to generate the table and generate an output. So in this case, I said save as a ping file. So what it did is it rendered it with its whatever native render is. By default, it's an HTML document, and then basically took a screenshot of it and dumped it in this folder. This generates a nice little ping output. You can do whatever you want. If you say PDF, it'll render it to LaTeX and then dump it as a PDF document. It can do lots of different things. I think it can even dump to like Word documents and stuff like that. Okay. So a neat thing with model summary is you can tell it to spit out a GT object and use all that stuff I showed on the GT slides to modify the table. So here I say, run a model summary of model list, set the output to the GT, and then pipe it into tab header, give it a title, give it a subtitle, and now that table from before has a nice title and subtitle. Okay. This is pretty cool. So if you want to modify and dress up your table, you don't have to use the model summary functions at all. You could use GT. So if you learn GT, you could modify these model summary objects and make really pretty tables with it. Okay. I say again, GT's LaTeX support is kind of crappy. Some days it works, some days it doesn't work, depending on what version they're on and pushing stuff up. Last time I was using it worked great, but I don't know what it's like today. But yeah, I think GT is pretty cool. Good way to do things. Okay. So another package is GT Summary. GT Summary is very similar to Model Summary. In fact, it works in a similar way. It works with Broom, GT, and Cable Extra to do flexible tables, okay? So GT Summary can produce model tables like Model Summary, but it can also do descriptive statistic tables for data frames. So this is sort of the reason I'm showing you this and not just Model Summary. GT Summary and Model Summary is kind of funny. GT Summary used to be called Model Summary, but the authors of Model Summary stole the name of it, kind of by accident, not realizing it. And so GT Summary had to change its name. There's a bit of a dispute between the author groups here, which is kind of funny. Anyway, these things happen. So GT Summary is a different way to do similar tasks. I actually like Model Summary syntax for most model tables, so that's just me. Okay, so GT Summary tables of, for instance, data frames provide some basic sort of descriptive statistical information. This is a common type of table you see in a journal article. If I say, in this case, take the MT-CARS data set, I'm selecting the first 9 variables arbitrarily, and then I run table summary. Table summary is GT Summary's function for summarizing a data frame. By default, what you're going to get is you're going to get frequencies for all the values of categorical or binary variables. You're going to get quantiles for your continuous variables, and you're going to get a sample size. So that MT-CARS data frame in table summary gives me this right here is a median and 25% and 75% quartiles for the MPG variable. These are frequencies for the cylinder variable with percentages. And then again, those quartiles for these continuous variables. And then these are binary variables where it gives you a frequency of 1s and a percentage of 1 values. Okay, and then it tells you what's actually being displayed here. You can customize exactly what it provides for all these with different arguments to table summary. The reason it shows these particular results is because in the discipline of the authors, and I forget exactly what it is, I want to say it's one of the biological sciences, these are the most common statistics they look for in like journal articles, so it just defaults to that. You can dress them up and change them however you want. But this sort of table is really common. Descriptive statistic tables are sort of expected in many disciplines and many journals, so you can generate them quickly using table summary and GT summary. Okay. A cool thing with this package is it can group these outputs for descriptive statistics too. So if I say, take my MT-CARS data, select those 9 variables, run a table summary, but say I want to do a table summary by a variable, it will do a descriptive statistic table for each value of that categorical variable. These are the descriptive statistics for the AM equals 0 category. These are the descriptive statistics for the AM equals 1 category. This is a really common side-by-side thing you might do in, I know in my discipline, we do it often. For instance, we might do sort of like a different breakdown by race or gender in individual level data so that you can say they're pretty comparable across these measures, maybe not these measures, or across 2 different data sets or something, right? You can display them like this and have them grouped out. This beats having to manually construct it. Okay. You can then, much like on the previous package, build on top of this using GT functions. So I took that table summary I did before. Then I say I want it to be a GT object using the asGT function. Then I added a spanner up at the top, a title, and then, or sorry, a header up at the top and a spanner here, transmission levels here. You can do all kinds of stuff like that. And here, as was asked earlier, can you do something like select multiple variables at once and not name them all? In GT, tab spanner, I said I want the spanner to go across any columns that start with stat. The reason for that is under the hood in GT summary tables, these things, columns are called stat. It's stat 1 and stat 2. If I say starts with stat, it ran the spanner across both of these columns. Okay, just a good thing to know if you do this yourself. Steal the code and modify it instead of having to like figure this out yourself. Okay, sorry, moving a little quick, but some lost time there to a lot of chaos. So I'm just gonna keep chugging along. Okay, one bonus here I want to show too is the core plot package and core plot function. This has nothing to do with model results. This is just for displaying correlations, but this is something I use all the time, and I just want everyone to know about it. So the core plot package, what you do, you load up library core plot, You say, I want a correlation plot of some correlation matrix. In this case, I've done a correlation matrix of the entire MT-CARS data set, but you can do whatever you want. This syntax here doesn't matter, just customizing it. What does matter is this is a way better way to display a correlation matrix than giving people a table. So my advisor, because he's a structural equation modeling expert, likes to see full correlation matrices for everything all of the time. This is what I give to him, and he loves it. He loves when I hand these things. This is a color-coded correlation matrix between variables. For instance, this is the correlation here between the cylinder variable and displacement. The correlation is 0.9. The circles get bigger and darker for stronger correlations. They're red for negative ones, blue for positive ones. They're, of course, 1 across the diagonal. So this lets you really quickly pick out what things are weakly or uncorrelated and what things are strongly correlated. Okay? This is a really handy thing. Don't use raw correlation tables. Stick them into core plot and look at it. It's way easier to see how variables are related doing this. Okay? Just know about it. Use it. It's one of my favorite packages and functions. It's probably my favorite package that does one thing. Okay. Okay, we're finally here. We are here to the last topic for the term, which is sort of normally about a 30-minute unyielding rant about reproducible research and best practices. So I'm just going to kind of burn through it. Okay. So reproducible research. Why is reproducible research important, and what is it? So reproducible research or reproducibility is not the same thing as replication. Replication, when we talk about things like a replication crisis, is not the same. Replication is when you run a new study to show if the results in a prior study hold, right? So if we rerun the same experiment or go collect new data on a population and run the same models on it, that's replication. Reproducibility is about rerunning the same study on the same data and just getting the same results. Reproducibility should be the lowest minimum bar for science to pass, that if you do the exact same thing to the same data, you get the same thing, okay? Reproducibility is pretty basic. Reproducible studies can still be wrong. That doesn't mean that they will replicate or anything. It just means that if you do the exact same thing the authors did, you get the same result, okay? Good reproducibility actually makes proving your studies wrong way easier. If other people can rerun your study and check your results, it's easier to show when you did things wrong, you made mistakes and things like that, which is important to science. Reproducibility means two main things. It means having transparent research practices. Anything you did, other people should be able to see what you did and repeat that process. It also means minimizing barriers to verifying the results of the things that you do. Your paper should have as few barriers as possible. Yes, we often work with limited access, restricted access data and things like that, but if somebody else can get access to that restricted data, they should be able to reproduce your paper very easily, okay? An important thing I want to highlight, and I always tell people all the time, any study which cannot be reproduced, any study which is not reproducible, is trustable only on faith. And I do not think that that is a good basis for scientific practice or knowledge. If you have to just assume people did everything correct and trust their results, that is not a really good thing. You can trust people because they're a big name, you know they do good work, but you should be able to verify the work that they did, okay? Non-reproducible science is, in my opinion, fundamentally ethically problematic for science, okay? Just putting that out there. Okay, so definitions of reproducibility. Reproducibility comes in, so here's a good one. Does this mean it's unethical for large organizations to not share how they got certain predicted estimates? Yes, yeah. If you don't tell people at least the methodology to do things, then you have no idea, and you're just trusting them. They could be completely lying. And I tend to default to the belief that if somebody doesn't share their methods for something, they're probably wrong. So yeah, normally it's kind of the thing where anything, oh yeah, I mean, sorry. No, great stuff. Yeah, no, if people don't tell you how it's made, how do you trust it? It doesn't make any sense, right? You have to take it on faith, and that's not what the scientific endeavor is about. I can understand if it's things like they can't share the things because the data aren't shareable, but give me some simulated data to show how the algorithm works. If you won't even show the algorithm, you're just making stuff up, as far as I'm concerned. I will assume they're making stuff up too. Okay, so reproducibility, 3 forms. Empirical reproducibility just means repeatability in data collection, right? This just means, so whatever is used to generate the data, it's documented and produces the exact same results when repeated, okay? Next thing is statistical reproducibility. This is verification with alternate methods of inference. So if you run a slightly different model, it reproduces, or you specify the model differently, it will be generally the same sort of reproducible results, okay? Sometimes this can get close to being replication if you take a wildly different approach, but normally this is just sort of like, if we change the convergence parameters and stuff, we shouldn't see big differences in output. You shouldn't see a difference in a paper coming out if you change the number of iterations in your like MCMC or something like that. The last one is computational reproducibility. This is reproducibility in the cleaning, organization, and presentation of your data and results. This isn't about running the models. It's not about collecting the data. This is about converting those like raw data into the displayed results in the paper, the memo, or something like that, okay? Is statistical reproducibility the same thing as robustness checks? Yeah, kind of. It's sort of an important thing to be doing robustness checks. Basically, yeah. You don't want your results to be highly fragile. Next one, how do you think about stochastic modeling through the lens of reproducibility, mostly about transparent methods? Yeah, it's really just about transparency. Make the assumptions, the things that were done clear. And honestly, we're always constantly making assumptions and choices when we just do our research. Just put them out there. Any assumption or sort of decision that's made that's hidden from people is bad. As a good scientist, you just put it all out there. If you give people everything, they're actually more likely to not even check at all. It's way more suspicious when somebody doesn't share things than if they're like, okay, here's everything. Here's my hundreds of crappy files, but they all run when you press one button, you can check everything. People are actually more likely to trust you then, but that's what it's really about. It might be filled with all sorts of choices, weirdness, things like that. It's about the transparency more than anything. And you do technically, for statistical sort of reproducibility, you really don't want your results to be highly sensitive to weird decisions, but if they are, you at least want people to be able to check those decisions and test them. Okay. So R as a language is very well suited to computational reproducibility. Python is equally well suited. These languages are great for automating all these tasks and making them clearly documented and put together. Okay, so I've been making you do reproducible research in R this entire term with all your R Markdown documents, not necessarily without even realizing it, because I think it's a good thing to learn and it's surprisingly easy to do in R. Okay, so computational reproducibility and thus R and Python will not fix flawed research designs. That's part of empirical reproducibility, and it won't remedy improper application of stats methods, which is statistical reproducibility. The thing is that empirical reproducibility, that is research design and also statistical methodology, are very difficult things which cannot be automated. That requires a lot of human decision-making, knowledge, things like that. Those are things you want skills in. Computational reproducibility, like cleaning, organizing, presenting your data, are things that as much as possible, you want to make your computer do it, so you're never manually doing your things. So you want to be devoting your time to knowing research design and knowing proper methods of inference, and then making the computer take care of as much of the computational stuff as possible. So the question, are R and Python codes interchangeable? They're interchangeable in terms of being able to do all of the same things, but their syntax is wildly different. So I would normally say learn one of them very well and consider picking up the other one later if you have a good reason. But it's probably not a good idea to try and learn both at once. Their syntax is a little bit different, and honestly, they perform the same tasks pretty similarly well. Okay. Yeah. So computational reproducibility is what much of this class has been about. The elements of computational reproducibility are shared data. People can't reproduce your work if they don't have the data used to generate that work. Shared data often has limitations because it's like restricted access and stuff, but you should do your best to share it so people can verify and replicate your work. Shared code is obviously necessary. You need to share the code that converts that data into the results so that people can see all the decisions you made to do it, right? So we're always making decisions about, oh, do we drop these observations? We keep these observations, we impute these observations, all these things. People need your code so that they can see the way that you did it. And also importantly, maybe see if you made mistakes. It's okay if other people catch the mistakes you made. The endeavor is about generating knowledge. If you're open, most people will be quite sympathetic if you make some sort of a mistake in a big, like lots of code or something like that, if you just own up to it. If you fight people who discover mistakes and things, or you try and hide them, you get a bad reputation quickly in your discipline if people find you out. Okay. Documentation is another important thing. So the operation of code in your project should either be self-documenting, that is incredibly obvious, or have written descriptions to make its use clear. Our markdown type documents are often sort of self-documenting, especially if you write a little bit of text in them. Okay, the last one, which I don't cover in this class, is version control. Version control is a method of documenting the research process or a software development process, and it's also a way to prevent losing work and facilitate sharing things. My class is up on a GitHub repository. Git is a method of version control that, in my case, stores things on GitHub. Okay, every change I've ever made to my class, even fixing every single typo on my slides and things, is fully documented. You could see everything I have ever done to this class from when I first created it on my GitHub repository. It's all there. If you want to see every bad decision I made in the design of this class, oh, it's all there for everyone to see. Okay, so with reproducible projects, their sort of levels of reproducibility vary. Back in the day, the most common level of reproducibility for papers was just go and read the article. Old school folks often will still use this as their level of reproducibility. They'll be like, I just ran all those things in the console by hand. I can't really reproduce it, but you're gonna have to trust me on the results. It's all in the article, okay? There are, in science disciplines, social science disciplines especially, this is not an acceptable thing. But there are disciplines where it is totally acceptable for this to be the level of reproducibility, like math. Right? You can literally have all things necessary to replicate a mathematical paper in proofs. This is a very rare thing in the social sciences, empirical social sciences anyway. So don't do this and get angry at people. It's okay if they tell you this. The next level is shared data with documentation. This is sort of the minimum at many major journals, like Science and places like this. You actually have to make your data accessible if it's not limited access, with some documentation of the data. This isn't the code and stuff, it's just the data and some documentation sort of explaining what you did. If you download stuff up like ICPSR, it's very common you'll get like a big explanation of how things were calculated and everything, but they don't provide any code to do. The next thing is sharing the data and all the code used to work on it. I think this is the minimum that we should do for all of our journal articles and things like that. At the very least, share what's possible. If you can't directly share your data, tell people how to get it and make it so your code files can work with those raw data. So if you have some restricted access thing from ICPSR, your code should be written such that if somebody drops those data directly into your directory for it, they press one button and it generates all your results. Okay, that's what I think should be the sort of minimum acceptable thing, and the way that in the future I'll be teaching my method students and things how to do it. Okay, and it's actually what you've been doing with your R Markdown documents. With your R Markdown, if you got the document and the data's there in the folder, you press button and you get results, right? So you already know how to do it. Okay. The next thing is an interactive document. This is actually an R Markdown document. This is something that weaves together the computation and the results and everything into a single document. It's a little bit beyond just the code, but it's not a super well-defined line. Above this are research compendia, which I'll talk about in a minute. And then the highest level is something like a Docker compendium, which is essentially a self-contained operating system. It's sort of like a miniature computer that replicates the computational environment that the paper was generated in. So even if the software changes over the years, people can go back and replicate it using the same version of the software you used to generate everything. This is really common in like the physical sciences and computer science and stuff like that. So you can use the sort of absolute control over the environment. Okay. So interactive documents, we've covered a lot in this class, right? Our Markdown documents, they combine code and text into a self-contained document. You would, in one document, load and process data, run models, generate your tables and plots, and then maybe fill in text values automatically. So here's the question. Is there a way to set the version of R to the version the code was created in? So you don't exactly set the version of R itself. You would actually have to have that older version installed, I think. You can set packages to their older versions, though. I would have to think about it. I feel like there might actually be a way to change R back. It may have a sort of memory for that, but I'm not positive. It's a good question. Yeah, I had to look it up. Yeah, Stata, you can do that. You actually might be able to in R. R doesn't usually change a lot across the versions. Like old R code is required to always work in the newer versions. They usually don't include breaking changes. So it's a good question. Okay. So interactive documents, like they let you let people inspect everything, right? So in essence, they're kind of self-documenting. So people can see all the code, everything used to generate everything, assuming they know R as well as you, they could see everything going on. Okay. Yeah, you could change the installed version in RStudio and mess with that, but the question is, can you like say run a command in one version of R and call on an older version syntax is sort of the question. And there probably is a way to do that, but I don't remember offhand. You could call individual packages as an older version though, in the library command. Anyway, basically by rerunning code, they reproduce your results. So they're inherently reproducible. Common platforms, right, R and Python. Research compendia, which I'm going to kind of move through quickly due to time, are portable, reproducible distributions of articles or other projects. This isn't just the like reproducible document, but it's everything necessary to generate it. So this will be an interactive document as the foundation, which will generate, say, the journal article itself. It will also contain files in some recognizable structure like an R package. There'll be the data, method, and output will be separated nicely. The data will be read only, and there will probably be a well-documented or even preserved computational environment like a Docker thing, okay? So this sort of encapsulates it. Sometimes people will distribute a journal article as an R package, and you just press one button to regenerate the entire journal article from the raw data. Ben Marwick in Archaeology packages his articles this way. RR Tools is a tool set built by Ben Marwick in Archaeology and some other folks to provide a simplified workflow to do this. If you're interested, I have a compendium up on my GitHub so you can kind of see what this looks like and works. Basically just an R package that generates an article. Okay. The book down package in R, which is part of RR Tools, but is also a separate, larger thing, is a package for generating documents in the proper format for theses, books, articles, and dissertations. If you've seen books like R for Data Science, that was written in Bookdown package, okay? Bookdown is an accessible way to write like whole book-length documents with nice typesetting and reference management without having to write any LaTeX. This is really nice, okay? You can integrate citations and generate automatic reference pages using like Zotero or BibTeX in this. It also supports HTML and PDF and Word document output, all that kind of stuff for publication like ready documents. So for instance, if you buy the print edition of R for Data Science and you go get the one on the website, they were probably actually generated with the same function call in R. Okay, this is sort of the amazing thing. You can generate a whole book ready to publish and a website with the same button using Bookdown. Okay, if you're generating a University of Washington thesis or dissertation, Ben over in Archaeology, who's on my committee, he wrote the Husky Down package, which will render UW thesis and dissertation format LaTeX documents using only Markdown and not writing any LaTeX. This is a really nice way to sort of bundle your thesis or dissertation into a reproducible framework, spit it out in the proper format, and never have to do any LaTeX or manual formatting yourself. Okay. So on to stage 2 rant, best practices and organization. So organizing research projects is something you either do accidentally and always badly if accidentally, or purposefully with some upfront labor. Uniform organization on your projects, that is making all your projects have the same folder structure and locations for things, makes it a lot easier to switch between projects or revisit old projects. You don't lose stuff, you're not confused about how they're laid out. I recommend something like this. This is an example kind of how I do it. Come up with your own system, but if you stick to it, it's really beneficial. The idea here is that there's a clear hierarchy. There's a top level folder for the project. All the written content is in a docs folder. all the code is in a syntax or code folder. The data is all in the data section where I've separated derived, that's like processed data, from the raw data, which is read-only and doesn't get messed with. The naming structure is uniform, words are separated by underscores, and all the names are descriptive, okay? Something like this, if you organize every project this way, you never lose anything and jumping between projects. It's easy to find everything, mess with your work. It's also easy for other people to find, okay? Do something like this, figure out your own system, but stick with it. Okay, so workflow and projects. So to summarize, the eminent Jenny Bryan, it's a good idea to separate your workflow from your projects. Workflow is stuff like what software you use to write your code, like RStudio, the location you put your projects, the specific computer you use, and any code you ran earlier or any code you ran into the console. This is your workflow. These are things you sort of do. They're not part of your project. The project includes things like the raw data, the code that operates on your data. You're gonna come bother me again? Good cat. Okay. The code that operates on your raw data, the packages you use. I got it. Okay. This is a cat. Okay. Oh yeah. I got a flu. She makes noises. Okay. There we go. Take the cat. Okay. So the project, for instance, is the data, your code, packages you use, and the output files or documents. Just take the, thank you. Okay. Okay. These should be separate. The idea is that your projects should not modify anything outside of the project. These things don't modify anything outside of it, nor should anyone have to modify anything to run it, right? Your project should be fully independent of your workflow, okay? So for research to be reproducible, it also must necessarily be portable. Portable software or projects is stuff that works independently of the workflow, which includes things like fixed file locations. So to facilitate this, do not use set working directory in your scripts or RMD files, because that will probably only work on your computer. Don't use absolute paths. Don't say data is in C:my project, because only your computer probably has that folder. The exception to this is if you have data on fixed immovable sources like secure data on a secure data drive, then it's fine to refer to it because that person's going to have it on some weird spot too. Never use install.packages in a script or an RMD file because that would make modifications to the person's computer and not just the project. And also don't use rm list equals ls anywhere but your console because that wipes other people's loaded files, okay? Don't do any of this stuff. Do use RStudio projects or the here package to handle setting working directories that work for everyone. Do use relative paths. So if I say read CSV /data my data CSV, if I move the project around, it will still go to the correct location based on the project's working directory. Do load every package you use with library. And additionally, this is a good thing to do, clear your workspace whenever you close RStudio so you don't accidentally use objects from your environment that are not loaded when you run the project. So in Tools, Global Options, Save Workspace, set it to Never. RStudio should delete everything that is loaded every time you close it so it opens up fresh every time. This enforces reproducibility. Okay, moving on. So often, you don't want to include all the code for a project in one RMD file. Most of the time, you got way too much code. This means it probably takes a really long time to knit the document, or the file is impossible to read because it's like 50 pages long. You don't have to put all your code in one file. There's two ways to deal with this. One, use separate R scripts or RMD files, which will save results from complicated parts of the project, and then load them in the main RMD. This is good if you're working with big data, you have to process it separately. It's also good for running models separately, and then you just load the results of them in the RMD so you're not rerunning them every time. If you have like a Bayesian regression model that takes 5 days to run, you don't want to put that in your knitting document so that every time you press knit, you have to come back 5 days later, right? Doesn't make any sense. Run the model separately, load the results in the RMD. Another thing you can do is if you have a lot of code, but it runs fast, you can use the source function, which will open up an external R script somewhere on your computer, run all the code in it, and then take the results from that and put it in the environment for the document. This is good for running lots of code that runs fast. It's also good for loading project-specific functions that aren't in a package. Okay. So I find it really beneficial, and I recommend that you break your projects into lots and lots and lots of files with little things in them. Few things in them, but lots of them. So you'll have scripts that have specialized functions you use for your projects, scripts that load and clean each set of variables, scripts that run each set of models, different scripts maybe that make the tables and the plots, and then one main RMD file that either runs these things when it knits or pulls their results from them to reproduce the entire project, okay? But all separate files. The nice thing about splitting your projects up this way is that once one portion of your project is done and it's in its own file, it's out of your way. It's not sitting there in the same file, getting in your way and making you scroll down the whole thing, blah, 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 right? It's totally out of the way. If you need to make changes, this also means you don't have to search through all your big files. If you want to make a change in some part of the process, go and open the file for that relevant part of the process, fix it, close it out, it's out of your way again. This means entire sections of projects can be added or removed really quickly, right? Or converted to an appendix. If you have a set of models that are all in their own little file, you can just move where those things get displayed in your R&D to the appendix or cut out entirely, and you don't have to like excise a massive pile of code or change dependencies, right? More importantly, in the greater world of software development, splitting your project up into lots of files is the only way to build a proper pipeline for a project. So I want to talk about pipelines. And I will note it's exactly time 5:20 now because I lost about 15 minutes to ridiculousness. I'm going to keep going. If you got to go, I understand. The recording will be up. But if you want to stick around, cool beans. Okay. So pipelines. Professional researchers and research teams tend to design their projects as what is called a pipeline. A pipeline is just a series of consecutive processing elements. These are things like scripts and functions in R, but you can do them in any language you want, okay? A bunch of sequential things. Each stage of a pipeline will have clearly defined inputs and outputs. That is, they take one type of object in one particular format, they spit out a different type of object in a particular format. They never modify their inputs, they just produce different outputs. And they will produce the exact same output every time they're rerun unless you change something in the stage, okay? So if you have things set up in a pipeline, this means when you modify one stage, you only have to rerun subsequent stages. You rerun that stage and the things that come after it. You don't have to rerun the earlier things. The things later are dependent on that, but the earlier things aren't modified, so you don't have to rerun them. This also means different people can work on each stage of the project and problems will be isolated within one stage, okay? If there's something weird going on, it's in one part of the project, it can be resolved there and somebody can be working on that stage, no matter what they do to it, because it always produces an object of one particular type and takes as an input one particular type of object. They can mess with it as much as they want, make their modifications and fixes, and it will still slot into the project the same way, okay? Another thing, and this is kind of a useful thing, if you have a project pipeline, it allows you to depict your entire computational project as what is called a directed graph of dependencies. This is a lot of big language to say you can do shit like this. Okay, the idea on a directed graph of dependencies is that you can map the entire project from your original input data to the output in a directed graph. A directed graph means the arrows always point in one direction, okay? So every stage of the project, the stages of the processing parts in this graph are an oval, and then the data that is generated are sort of these file-looking things. The idea is that you can take some unambiguous input, like these are your data files, your CSVs. You have a script that loads the data. It then puts out my full clean data. I have one script that generates descriptive statistics and generates a descriptive statistic table. A different script reshapes the data for my models, puts them into the models, and then the model script generates a plot from my models and maybe a table for my PDF. My RMD file knits together all of these components and spits out a paper, okay? This is an entire process for going from the raw data to the output. When I give seminar talks, and including the job talk that I gave at Oxford here in September that got me the job, I created a complete graphical dependency graph like this of my entire dissertation chapter so that they could see unambiguously how the entire project went together in one picture. People love this kind of stuff. You don't necessarily need to do it, but sometimes in a journal article, something like this can be really nice. You might not need to show the processing steps, but if you show like you began with this data, has this many observations, I made these changes, the observations drop or the units change, and you have like a directed graph. I've always found reviewers love this kind of thing. It's a nice way to think about it. It just kind of depicts what's going on. This one's a little cluttered because I wanted to make it big enough to read and fit on here, but you can just make it more or less a straight line. Okay, in big projects, especially like within companies and things like that, these directed graphs can be really, really large and complicated. But the neat thing is you always know what's going on. You know, for instance, if you change something in model R data, you're going to have to update, like, or sorry, not the data here, but if you change, yeah, actually, if you updated the data here, you need to run the models again, regenerate this and knit the document, but you don't have to modify the descriptives or regenerate this table, because only the things downward in the arrows need to be changed. If some of these things take days to run, this is really important. The neat thing is, if you use something like the Drake package in R, it can automate the generation of graphs like this, and it can also automate rerunning dependencies further in it. Drake knows, for instance, that if I modify this reshape data.r file, it has to rerun all subsequent things, and it automates the entire process. So if you're in really complex projects, something like Drake is really nice. Okay. Just about the last little thing I want to say. On formats, this is philosophical. This is purely philosophical. This is like one of the most, discard this if you don't like this advice for you, but if you're curious what I think about these things, you're stuck listening to me. Okay. So I say you should avoid any closed formats or commercial software formats of like file formats and software wherever possible. Commercial products are sort of fundamentally bad for science in some very particular ways. The issue, or the thing you should do instead, is use open source software and open source file formats. You might be like, well, why do this? R, for instance, is an open source piece of software with open source file formats. This is always better for science. I believe firmly that people should be able to explore your research results and methods without buying a piece of commercial software. There should not be $100 or $1,000 barrier between people and reproducing your research results. You don't want your research to be inaccessible also when the software is updated. This is an annoying thing that sometimes happens where somebody will like update like SPSS and actually break compatibility with past versions. This isn't really ideal. Stata is actually pretty good about it because it does let you rerun sort of older versions of Stata within it, but older versions of Stata can't run newer Stata code, so at least there's some breaking going on. I actually think Stata is a great piece of software. I'm not one of those R people who's just like, Stata is terrible. They've never used it seriously. I have. I was taught in an econometrics program, so I use Stata a lot. It's really good for some particular things. I just prefer R. Okay. Another thing, open source software is sometimes actually just better. Not just better for science, but it's actually better software. The reason is a lot of open source software is updated way more quickly. It tends to be more secure because you have the eyes of all of these security-oriented programmers on it all the time. And open source software just like almost never gets abandoned. One of the wild things is like, if you look at the pieces of like Unix software that are still in common use, like Emacs or Vim, people are using these like 40-year-old pieces of text editing software, and they're religious about using them and keeping them updated and running. Open source software usually just, it doesn't die. It very rarely dies. People keep it alive forever. They're passion projects and things. They're not relying on money for it. They tend to last forever, okay? R is one of those things where it's always been open source software. People are passionate about it. It's gonna be basically eternal. I mean, it'll probably, I mean, one day it's going to, you know, the popularity will decline. It's still on its uptick right now, but you know, it's eventually going to decline, but support for it will probably basically exist for a really long time. I can't necessarily say the same thing, like commercial companies, they can go out of business and the product just sort of disappears. I like Stata a lot, but God forbid they go out of business and the product isn't maintained anymore, it's going to be deeply problematic. Okay. Stata, however, is semi-open in that software routines in Stata are still written by common users, and so some support for it will probably always exist. Anyway, The ideal, in my opinion, is to try and use software that reads and writes raw ASCII text. It works with plain CSV files and TXT files. That's the thing you want. Avoid binary formats. Word documents, no. Okay. So, speaking of text, writing and formatting documents, and this is something that we have been misled by our terrible educations of like word processing documents through grade school and middle school and everything. We have been led to believe that writing and formatting documents are somehow the same job. Up until well deep into the 20th century, there used to be writers and there used to be editors and typesetters, and they never did each other's jobs, okay? Somebody did all the writing, they handed it to somebody else whose job it was to edit through these things and typeset it and put it out somewhere, separate jobs. Software like Word lies to us and makes us think that these are sort of one job you do together, okay? Don't do that. I highly recommend you do your writing first, completely separately, basically finish all your writing and worry about formatting later. Markdown was actually made for this. The point of Markdown is you have very little formatting to do. You might italicize or bold something like that. You maybe say a header, but you don't mess with things like indentation, spacing, paragraph breaks, any of that kind of crap. That's all done on the rendering side after you're done writing, okay? You do all your writing, you don't care about format. Word processors like Microsoft Word try to get you to do both at the same time, usually badly. They make you do things like waste time by leading you to format instead of writing. Being like, well, I don't like the way these headers look. Maybe I'll bold them, italicize. Maybe I'll put them all caps. This is just a way to get you to waste lots of time. That's not really purposeful, but naturally as humans, we're really good at finding ways to procrastinate. Messing with formatting is one of the best ways to procrastinate while writing, okay? If you use a tool that doesn't let you do any of that, you can't. Okay. I recommend you find a good modular text editor and learn to use that for things, okay? I like Atom, it's GitHub's text editor. Sublime is a commercial one, but it's pretty good. If you are an old school programmer already, you already know about Emacs and Vim. If somebody tells you to learn Emacs or Vim and you don't currently use them, run away from that person. Just don't use these things, okay? So, last thing I want to mention is version control. Version control is something which originates in collaborative software development. The idea of version control is that every change ever made to a piece of software is documented, saved automatically, and revertible. You can go back and undo any change you've ever made to any set of documents or code, okay? Everything ever done is recorded. Version control in research projects allows you to document every decision ever made in the entire project from the origin of the project, okay? If you're constantly doing version control and updating your things, you can see everything that was ever done, okay? This is basically where the idea of like track changes comes from in a Word doc. Track changes is baby's first version control. Actual version control tracks literally everything in documents, every modification to data, files, you name it, okay? Version control can protect your work from destructive changes. If you accidentally have ever like deleted the contents of a Word file, saved it, and not been able to recover something, this is literally cannot happen in proper version control because you can revert the changes. The documents are actually still there. Every version of them is recoverable, okay? You can also simplify collaboration with version control because version control automates merging changes. If different people are modifying the same files, it can merge them together, which is kind of nice. This is good for big software development projects because everybody's coding on things at the same time. You have to be able to merge things in together all the time, okay? It documents any design decisions that were made because everything is seen and visible. And of course, the big one just makes your research process transparent. You can see everything someone ever did in a project. So if people are really curious, they can go back and see everything you ever did. This is good for science. Terrifying to some people not used to this paradigm. The idea everything you ever did is visible and naked to the world. The thing is most people don't care that much about you, so they're not going to dig down through your GitHub repos and stuff like that. But if they really want to, it's nice for it to be out there because they're usually doing it because they care, either about your work or about you. Okay. Anyway, Git is the dominant platform for version control. GitHub is a free platform for hosting repositories, Git repositories. So a repository is a folder on your computer where every change you make to any file in that folder gets tracked by Git, okay? Once you're satisfied with changes you make to some files, if you're using Git, you commit these changes and then push them to a remote repository, okay? So the idea with Git is you press a button, it uploads your changes, all your files to this remote repository, thus automatically backs up all your files. I could have all 3 of my main computers catch on fire simultaneously, and I will lose literally nothing because my life is pushed to GitHub, okay? And if GitHub gets blown up, I actually also have cloud storage on a different platform. So here's a question. Would you recommend using Git for classwork as well? Yeah, I actually have uploaded homework assignments in my project directories up into GitHub just because sometimes it's convenient. And what should be public on GitHub is a great question, which I'm going to get to a little bit here in a minute. Okay. Okay. So once things are pushed to a repository, if the repository is public, other people can just press a button and copy the project. My CSSS508 class, every piece of content in the entire class, you can press one button and download every file in my repository. And what will come with it is a complete record of every change I've ever made to this class, okay? It's all there, it's public. If you want it, take it. Modify it too, okay? So you can also permit other people to make suggestions for fixes and changes. I've actually had people suggest fixes and changes in like projects I'm working on in my class, stuff like that. You can do it. You can recommend them if you enable people to do so. Okay. Constantly committing and pulling changes automatically generates sort of a running history of the evolution of a project you're working on, because you can see every time something was committed to a remote repository, you can see how the project develops, how things are added to it, how things are modified. Okay. Every commit essentially gets logged as a change, and you can revert these changes, browse through them, that sort of stuff. Okay. So Git is already integrated into RStudio under the tools menu. You have to do a little bit of setup. I highly recommend Jenny Bryan's. I think this link actually goes to, yeah, Happy Git with R, Jenny Bryan's setup instructions for Git in RStudio. There's also a GitHub desktop application. I actually use the desktop application because I suck at giving Git commands through the console, and I just want to let the GUI take care of it for me. I'm not a sophisticated Git user. Okay. So this is about what should be public on GitHub. Okay. So beyond archiving your projects and allowing sharing, GitHub can also serve as a sort of a CV for programmers and scientists who do programming. Okay. The idea is that by allowing others to view the projects you've done, you can display competence in programming and sort of research in general. If people can see all the stuff you have up, it demonstrates competence. If you're planning on working in the private sector, an active GitHub profile will give you a leg up on the competition, and in some disciplines, it will be an expectation. So if somebody's applying for like a computational social science position in my department, if they don't have a GitHub profile, I will be very suspicious of the seriousness of that candidate, because it's sort of like just an expectation that people that do serious computational work are going to have like a GitHub or GitLab or some other public repository sort of account. Similarly, it'd be really hard to get a job doing actual programming in any legitimate company if you don't have publicly available code for people to look at. Okay, unless you're being hired by truly incompetent hiring people, but like I said, serious companies. Okay, if you're aiming for academia, GitHub is special in that it will, having an account with stuff on it will signal technical competence and also an interest in research transparency if you have your research projects up there. It shows I am an open book, the work that I do is open. People who care about reproducible research are gonna see that. I would put it on your CV. If you look at my CV, it has a link to my GitHub on it because I want people to go look at it because it conveys that I'm serious about this stuff. My stuff is open and I try and make contributions with like available software, okay? Yeah, so as far as what should be public on GitHub, anything you want people to see. It's really, if you're proud enough of something that you think people might want to like browse and look at the code, I would do it. And just, you know, it doesn't matter if it's something, just maybe don't put things you're really embarrassed by up there. I have some things I'm embarrassed by, but I just default to making everything public. I don't think people care enough about me to seriously browse through all of my code, except a couple of my friends. That's fine if they make fun of me. Yeah, let's put stuff up there, but it's a good idea and it's a good practice to get it. I highly recommend it. And you know, it's just kind of a neat thing to do. It's a good thing. It's a modern kind of thing that I think people should be doing. Okay. Anyway, last thing here. Finally, 20 minutes over time. Let's wrap up the course. Thanks for sticking with me through all the technical difficulties today. If you're watching on video, well, No thanks for not coming today. Okay, so what's going on? What you've learned in this class is actually a lot of stuff, or at least I hope some of it sunk in. I think I said earlier in the term, my class is a little bit like a fire hose. I spray out there, you take sips from it, you're not going to get all the information, but we did go over a lot of stuff. A lot of water got hosed out there. I hope you got some of it out of it, and I hope you can go back to these things. We learned things like getting data into R from many formats, manipulating and cleaning data, visualizing it, doing loops, writing functions, doing our markdown documents that combine all these things into one file. And we also got some special topics like working with strings, working with spatial data, talking a little bit about reproducible research today, model results, things like that. Really a lot of variety here, probably more than my intro class should cover, but I am not good at trimming things down. So we covered a lot of things. And hopefully you'll at least remember you can look these things up using these resources or other things when you don't remember how to do them. And I'll say right now, I routinely do not remember how to do things I sometimes have even covered in this class, and I look these things up. Don't be embarrassed by that. It's literally impossible to remember how to do everything unless you're like David Robinson or somebody like that who's like does YouTube videos on R for a living. Okay. So what comes next for you? Obvious next step for many people is going to be learning more statistical inference. Now that you've taken this class, you should be much better positioned to take those classes in stats without trying to simultaneously learn R and learning the stats at the same time, which is deeply traumatic to most people who try to do it. I know because I learned R through these stats classes. I didn't know what I was doing. It was really, really unpleasant. And I don't want that for other people, so that's the reason for this class. And then you can use tools you learned in this class to make your life easier and easier in those classes and the results from those classes more powerful by doing things like, for instance, the stuff I showed with model results today. Display these things better. Use GG effects with the models you learn in those classes, blah, 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 right? Take these things, apply them in those classes. And I highly recommend taking those classes too, because they'll keep you in the game with regard to writing your code. If you put this stuff down for a lot of time, you're going to start to lose things. Figure out some way to keep up with it. Taking stats classes is a good way to do it, and you get some stats trained at the same time. Next thing, same thing, practice. Do lots of things. If you don't have anything else to do, I recommend replicating things you've done in other packages like Excel, SPSS, or Stata. Just try and get the same results out of them in R, okay? You replicate, you'll feel good if you get the exact same results out in R. If you get different results out, you may actually have discovered mistakes. I've done this before. I like to take projects and at what different stages I will rewrite my projects from the ground up, like just completely rewrite a project. And I've discovered critical mistakes in my work before, even as recently as the last few months, by rewriting my projects. It's a good thing to do periodically. Replicate your old stuff. Just think about it too. Think about how you can use these things to work with your data, experiment with it, try new methods. Use our markdown documents for your homeworks and stuff going forward. Maybe consider writing your lecture slides if you TA for a class or something like that. Maybe try doing them as our markdown documents just to keep in the game, right? More advanced stuff would be like stuff we talked about today. Pick up version control, use Git. Maybe do things like learn how to do interactive web applications using Shiny. It's actually surprisingly easy. Do things like write functions, make your own package, okay? Do something in here to keep yourself in the game so you don't start losing these skills, okay? So some plugs for future stats classes. If you got no stats background at all, I strongly suggest starting with something like SOC504 Applied Social Statistics. It's a good like intro to graduate level stats. If you have finished a stats sequence in your program, for instance, the SOC sequence or poli-sci sequence or something, the next step for most people is usually CSSS508 Maximum Likelihood by Chris Adolph in the autumn. It's a really good introduction to maximum likelihood. And maximum likelihood is sort of the underlying method in just about every common, more advanced statistical routine. And likelihoods are also a really important part of even Bayesian stats. So if you learn to get good at likelihood, it kind of covers everything. Visualization, 569 Visualizing Data is another Chris Adolph class on visualization. It's the easiest CSSS class probably, but contains a lot of really useful information on visualizing data, including a lot of like cognitive science on how people actually see and understand the pictures, okay? If you want to study event or duration data, that is the time until something happens, or even like the number of times things happen in a specific period of time, event history analysis is a class for that. Event history analysis also has a really good introduction to maximum likelihood estimation, so it's kind of good for that. If you're going to work with network data, when they offer it, the social network analysis class is pretty good. I don't know how often it's been offered. If you want to work with spatial data, 554, Spatial Stats by John Wakefield, is a great so geostatistics or spatial statistics class. It's hard though. I do not recommend it's like your first advanced stats class you take, but it does cover sort of a really broad range of geostatistical methods and applications. And then sort of my last plug here is working with time series data. There's actually 2 different time series and panel data classes. Chris Adolph's is for fewer units like individuals and more time periods that they're observed in. Elena Arosheva's focuses more on fewer time periods and more individuals. So either one. I also would recommend literally any class by Elena Arosheva on there. She's an absolute gem of a person and teaches great classes on things like dimension reduction in her multivariate statistics class. What's her other one is, she does one of the time series and panel data ones, sometimes does some other stuff. Anyway, a lot of good people in CSSS. If you got questions about other classes, let me know. I've taken most, but not all of them. Okay, and with that, that is the conclusion of our term. I greatly appreciate all of you sticking with this class the whole way. I know sometimes it can be kind of daunting. I try and make it as minimally traumatic as possible. Yeah, that's all I got. You got no homework to do next week or anything like that. You're done. Feel free to look me up in the future if you need help with stuff. You know, if you run into problems you get really stuck with, shoot me an email. You know, I really don't mind. I answer a lot of emails pretty regularly. I usually by the end of class, I will have gotten a couple more already. And I just answer my shoot back. I have fun with it. And I want you to have fun with it and get better at this stuff. Hit me up anytime. It's been a pleasure having everyone. I'll try and get grades done real soon, but unless you didn't turn anything in, you probably passed the class. Don't worry too much about it. If you're worried about it, do shoot me an email. I do allow you to turn in homeworks as late, basically, as you want. So if anything you want to turn in, just do it in the next like 3 or 4 days. Get on it. So if you got any questions, let me know.
Hey, Chuck, I do have one quick question.
Uh-huh.
It looked like when you were doing the GT table and redressing it, like I didn't see your code when you modified the table a bunch in the slide set.
Oh, yeah. And so are you looking at the PDF?
Yes.
Yeah, and so this is a thing that's kind of funny. You'll notice how the number down in the slides isn't changing as I update this.
Mm-hmm.
So when the slides are rendered to PDF, it actually renders them based on their page number. But because I have all this inside of one slide, it doesn't do the stepped changes.
Okay.
And that's just a limitation of the PDF rendering. So I would just, take a peek at it on the HTML docs for these sort of sequential things like that. There's no way for me to overcome that within this sort of slide framework I'm using. It's sort of dumb, but I don't have any control over it.
Yeah. Okay. Thanks so much. Really appreciate your help.
Absolutely.
Yeah, seriously, thank you a bunch. It was what I look forward to every week.
That's great to hear. Just yeah, I had a lot of fun with this class, and I will miss teaching it in the future, but I'm sure someday I'll resurrect it. So we'll see.
Will it be taught after you move on?
Yeah. So I'm not. It hasn't been fully confirmed, but I have suggested a person to pass it on to in my department because it hasn't confirmed. I won't say, but yeah, I have suggested somebody who is not a statistician or a computer scientist, somebody who has a background like me, who understands the sort of trials of learning this stuff. But I have suggested somebody to pass it on to. It'll be a learning experience for them, but I actually learned much of what I know by teaching this class over the last like 5 years. Mm-hmm. So it's a good experience for somebody else. So the class will continue. And in fact, they'll probably use my materials or base off of it, but I'll be gone.
Okay. And then one technical question based on the lecture today. I'm one of the people who's slightly nervous about version control. Mm-hmm. It kind of sounds like a keylogger in some ways. And so it's not that, because I was wondering about accidentally like disclosing protected health information when you're working on a project, like maybe your data set's de-identified, but you're doing something else. And
yeah, so the trick is if you have restricted access data, you don't put it in the repository, is normally what I would do, and then it can only update things in the repository. So kind of as an example, it's probably, I can't really zoom these things, can I? No. So for instance, this is the folder Yeah. Yeah, I can't really increase the text size on
That's
here.
I can read it.
Okay, you're good. Yeah, so this is this is essentially the folder for my CSSS508 class, which is a repository, right? If you go onto GitHub and look for at this class's GitHub repo, every single file in here is in there, except for a few. So if you look, you'll find that things like this ignore folder, which is what I store the homework keys in, is not on the repository. Because what you can do is there's a git ignore file like this. You can open this up, and this specifies things you don't want to be loaded onto the repository. So for instance, I'm saying here, like, I don't want my old lectures on the repository. I don't want these improvement notes because I take the notes from like the student evals from the class and I figure out what I want to improve, but I don't want that in the repository. The ignore folder. This here are my Twitter credentials. I don't want other people to be able to log on as me in Twitter. So I set more my Twitter credentials, that sort of thing. And also big files. Like I have some really large files that won't fit on GitHub. So I ignore them too.
Thank you. Yeah.
You can do that. And so it's not really, so what gets synchronized is what you tell it to synchronize. So you essentially will make changes and then you have to manually push a button or something to upload these changes. Right?
Okay. Nice.
Yeah. You've got full control over it. And very often I have projects that have restricted access data, but I just don't want to share it. And so I don't. So these are all like GitHub repos that are up on my GitHub. And some of these contain data that's restricted access. There's a ton of restricted access data in here. I have stuff that's using like restricted access police data. In here, I have it set to ignore my data folders of raw data here. So all my raw data is like Seattle Police Department data, a census of like homeless encampments in the city and stuff. This is not uploaded to my GitHub. I just block it out.
Nice. So you got to be careful, but once you do that, okay, that's really helpful.
Explicit with it. Another thing you can do, and this is what the main thing I kind of do, is my real restricted access data, the stuff I sign data agreements for, is actually on a external encrypted hard drive. And because it's not in the repository, that stuff could never be uploaded to GitHub.
Gotcha. And so for like reproducibility, you just have to, you've got to work around that somehow.
Well, yeah, what you do is you'd have something like at the top of, you'd make it so there's exactly one script file that does the loading of all the restricted access data. And it has at the top a single like field that the people reproducing it can just change the location to where their restricted access data are and then handle it.
Yeah, and call it out like that.
Yep.
Nice. Cool. Thank you. I really care about these workflow issues in a way that I think when I try to talk about them with other people, they get frustrated that I care about them.
Oh yeah.
but like, yeah, thanks for indulging my weird questions. So
yeah, so if I go to like if you want to get an introduction to it, I highly recommend this. This is Jenny Bryan and Jim Hester's Happy Git and GitHub for the User. This is a good introduction to Git and GitHub for our users, and does have some general information on, for instance, why would you use Git and why would you use GitHub?
Okay.
Yeah.
Nice. All right. I'll let you have your evening. Thank you so much.
Okay.
And Elliot says hi.
Yep, I see.
Yeah. Yeah, Chuck hasn't missed you. Don't worry.
Okay.
All right. Take care.
Bye-bye.